Hey guys, it's Miss Peters, and today I'm going to go over average atomic mass and mass spectroscopy with you to review and make sure that you have everything. So first, just a refresh that the type of element something is determined by the number of protons, which is the atomic number. On the periodic table, that's the number up top. So if something has one proton, it's hydrogen, no matter what. Neutrons and electrons don't affect what type of element it is. And then when protons and electrons are equal, our atom is neutral. If the atom is not neutral, that means it's an ion, and an ion is something that has a charge because there's an imbalance of protons and electrons. If the atom has lost electrons, it's now a cation and it has a positive charge. That's typically our metals. If it's gained electrons, it's now called an anion and has a negative charge. So that should be a review. Key thing, number of protons determines what something is, not neutrons, not electrons. And then on the periodic table, just to refresh, this top number is protons. The bottom number is the average mass, and we'll talk about that in a minute. So if something has 9 protons, 10 neutrons, it is fluorine because fluorine's number 9. If it has 9 protons, 2 neutrons, it's still fluorine because it has 9 protons. Okay, the atomic mass of an element is the number of protons plus neutrons. Electrons don't really play into the mass. They do have a mass, but it's so small we can ignore it. And an isotope is an atom of the same element that has a different mass number because they have different numbers of neutrons. Most often you're going to see isotopes written like these down here, carbon 12, carbon 13, carbon 14. That just means carbon 12 has a mass of 12. Carbon 13 has a mass of 13. Carbon 14 has a mass of 14. And all carbon has 6 protons because it's carbon. And so that carbon 12 must have 6 neutrons because protons plus neutrons equals the mass. That carbon 13 then has to have 7 neutrons. 7 plus 6 is 13. And then carbon 14 must have 8 neutrons because 6 plus 8 is 14. You might see isotopes written in this format. I don't really think you'll see it, but element symbol, mass number up top, atomic number at the bottom. So with that carbon example, it would be like C6. That would be carbon 14 versus carbon 12. And remember, the difference is their number of neutrons, not their number of protons. Okay, so nitrogen 14 and nitrogen 15. How many protons and neutrons are in there? Well, nitrogen, all nitrogen has 7 protons because it's nitrogen. And so nitrogen 14 must have 7 neutrons because 7 plus 7 is 14. And then nitrogen 15 must have 8 neutrons because 8 plus 7 is 15. The average atomic mass is the mass on the periodic table, and that is an average or a weighted mass of all of the isotopes of that element. You learned this in 10th grade. Doesn't mean you remember it, but we did learn this. And the formula is average atomic mass equals mass of the isotope times its percent abundance plus mass of the next isotope times its percent abundance for however many isotopes there are. And so I'm going to make up an example. Let's say element X has 2 isotopes. One of them has a mass of 12 and is 40% abundant. And then element X, the other one, is mass of 14 and it's 60% abundant. How you would solve that is the average mass equals mass of my first one, which is 12, times its percent abundance. So you're not going to write, if you don't remember, 12 times 40. that percentage you need to change to a decimal. And if you don't remember how to change percents to a decimal, divide it by 100. So 0.4. So 12 times 0.4 plus 14 times 0.6. And if I type that in, which I didn't type that in earlier because I just made this up, 12 times 0.4 is 4.8 plus 8.4. That average mass is 13.2, which, looking at those two isotopes, that would make sense that the mass is 13.2 because most of that fake element has a mass of 14. And so the average atomic mass should be closer to 14 than it is 12. And so we're going to do an example. This was from your Nearpod yesterday, but with this, I wanted to go over it because the sig figs are kind of tricky. So neon has 3 naturally occurring isotopes. Neon 20 has a mass of 19.992 AMU and abundance of 90.48%. Neon 21, mass of 20.994 AMU and abundance of 0.27%. Neon 22, mass of 21.991 AMU and abundance of 9.25%. Notice the exact atomic masses for each isotope are provided as opposed to only their mass number. So what's the difference between a mass number and an atomic mass for an isotope of an element? Well, mass number is that, oops, I meant to highlight that, not right. Neon 20, that's the mass number. 22, 21. Mass number is really just protons plus neutrons. The atomic mass is like the actual mass. Protons don't actually weigh exactly 1 AMU. But for the sake of most of our problems, and when we talk about it, there's no need to say neon 19.992. That's why we use mass number, but atomic mass is more exact. And if you have both, as you do here, which one should you use for the average atomic mass calculations? You should use the actual atomic mass, not the mass number. It is more exact and will give you a more exact answer. So, unless if you get the actual mass, use that. If you don't, use the little mass number. Okay, and then number 3, we're going to calculate the average atomic mass for neon using this data. And then I'm going to go over with sig figs how to do it. Now remember, I told you 99% of the time, if you look at the problem, and so looking at this problem, the number with the least amount of sig figs is 0.27. That is 2 sig figs. So if you answer to 2, you're probably going to be fine. The AP test is not very strict about sig figs at all. If you're supposed to have 2 and you answer with 3 or 4, it's fine. Don't ever answer with 1 sig fig unless you're really sure it should just be 1, but they aren't going to murder you for sig figs. They care that you know the chemistry, not that you know sig fig rules. So I really don't want you to stress about it, but I am going to go over sig figs with this problem. Okay, so average mass equals mass of the isotope. So the mass of my first isotope is 19.992 times that percent abundance, which is 0.9048, plus mass of the next one, which is that 20.994 times that percent abundance. Now anytime it's less than like 1, I have to go divide it because I'm always scared I'm going to mess up my zeros. And so 0.27 divided by 100 is 0.0027. You might be able to do that in your head. I always double check. And then the mass of the last one plus 21.991 times 0.0925. Okay, now for the sig fig part, because I do want to go over that. The rule, we have to do the multiplication rule first. And the multiplication rule is when you multiply, your answer should have as many sig figs as the least amount of what you're multiplying. And so for this first part, 19.992 has 5 sig figs, 0.9048 has 4. So when I multiply those, my number should have 4 sig figs. 20.994 has 5, 0.0027 has 2. So when I multiply those two, my number should have 2 sig figs. And then these last three, that one has 5, this one has 3. So my number should have 3 sig figs when I multiply those. I'm going to go to the next slide to do the rest of it because I clearly have run out of room. Okay, and so when I multiply those, the answers with sig figs are 18.09 plus 0.0057 plus 2.03. And make sure you are following your rounding rules. I think it was that number when you type it in, it's like 0.00566. Well, that makes it 0057. Remember, the 6 rounds that up. So you should follow rounding rules. And then now I'm adding. And the rule for adding is you go by the least number of decimal places. And so this one goes to the hundredths, to the, what do you call after a thousandth? I don't know, 4 decimal places. And then this one goes to the hundredth. So our answer, when you add, should go to the hundredth. And when I add those up to the hundredth, it is 20.17. And the unit for atomic mass is AMU. Now, if you went by the rule where I said it works most of the time, 2 sig figs, you would have to do something funky like 20 with a decimal place. I don't know, it gets weird, and so then you would probably just want to do 20.2 AMU because it's really hard to make 22 sig figs, and then that would be 1 sig fig off, not a big deal. But again, the AP test is not going to kill you over that. You're not going to fail the AP test because you did sig figs wrong. You're going to fail the AP test because you don't know your chem. So know your chem. Sig figs, don't stress, really. And so mass spectroscopy. Hopefully you watched that video in the Nearpod. It explained how it gets there. It is a graph that shows the masses of individual isotopes. In this graph, the mass number is always the x-axis. So this is something with a mass that has an isotope with a mass of 10 and an isotope with a mass of 11. And then the y-axis might show the relative intensity or the percent abundance. And so you need to just make sure you check what the y-axis shows. Most of the time you will see percent abundance, which is just like we do with average atomic mass. You know, the percents add up to 100, super easy. So this one, we're actually going to, no, we're not doing this one later, but like 90's got a mass of about, that one with 90 is about 50% abundant. 91 is, I don't know, 12% abundant. You would just read it like normal when the y-axis is relative abundance, which is what you should see most of the time. Now, you might see, I don't want to say you won't ever see it, a y-axis that is relative intensity, like this example on the left. I'm going to erase this. Now, something in your head should go off when you see this, because you should see that boron 11 is at 100, and then boron 10 is at 25. You can't have 125%. That's not how percents work. And so if you were to see relative intensity, the best way to do it is look at the graph, write down the numbers. Okay, so if I had 125 atoms, and I'm getting that number because 100 plus 25 is 125, that means that 100 out of the 125 should be boron 11, which is what percent? That's 80%. And then 25 out of the 125 would be 25 divided by 125. I keep typing that in wrong. That would be 20% abundant. And then you could go on and solve the problem like normal. And then I just realized you might be like, Miss Peters, how did you know that was boron? I know that's boron because boron has an average atomic mass of like 10.8. But I don't expect you to know that because you don't have average atomic masses memorized. So you wouldn't know that was boron. I do. Well, if you checked your periodic table, you would. I do because uh, I teach chemistry. But if you checked your periodic table and you're like, what has a mass between 10 and 11? It's boron. Um, so just make sure you double check your y-axis. If it's not relative abundancy and it says relative intensity, you'll have to do a little math. Not hard, but just change it to percentages. And intensity should always be over 100 when you look at the numbers, so that should set something off. And relative abundance, to make sure you read the graph right, your abundances should always add up to 100. So let's say you read this graph and you got 105%. Well, you read one of them wrong, so go back and double check yourself. Okay, and we can calculate average atomic mass. I just showed you how to get percents. So the 10 was 20% plus the 11 was 80%, not 0.08, 0.8. And when we calculate that, 2 plus 8.8, that is 10.8. Go to your periodic table, that's boron. Mu. And where is boron? Yep, 10.81. And again, you get a periodic table, so don't think you have to memorize these. And periodic tables are really helpful when you do average atomic mass calculations, because let's say you're looking at a graph of nitrogen. Nitrogen has a mass spec graph of nitrogen. Nitrogen has two isotopes, 14 and nitrogen 15. Well, if we look at the average atomic mass of nitrogen, it's 14. So if you read that graph and you say like 70% of nitrogen is 15, you did something wrong, because most nitrogen is nitrogen 14, because the average atomic mass is 14. So use your periodic table with average atomic mass and mass spec to help you. Okay, and then we are going to do this problem together. This is straight off an old AP test. This was, I think, a free response question. Okay, so the mass spectrum of the average sample of a pure element is shown in the figure above. Which of the following is the identity of the element? So looking at my y-axis, it is percent abundance, which means those are the percents. So it's not the intensity issue we had before. And reading this graph is kind of tricky, but 90 is at a little above 50. I don't know. It's kind of 55, but let's look at the others. We'll write 55 for now. 91 is at like right above 10. Maybe it's 12. And then 92 and 94 are right at the same, and they are like a little below 20. So let's say they're 18 and 18. We'll go to your calculator, double check what does that add up to, because percents have to add up to 100, and that equals 103. Well, I know the 91 is above 10, so I don't want to lower that number. And 92 and 94, they're almost to 20, so I don't want to lower those numbers. So I'm going to go ahead and just lower this to 52. And this isn't an amazing graph, because that gets me 100. So they wouldn't be like, wow, I thought 90 was 53% and you said 52. That's wrong. They would, however, if you left it at a total of 105%, they would think something's off with that. So if the graph is kind of unclear like this one, just make sure your percents add up to 100. And then I want to find the identity of the element. Well, I can find the identity of the element by finding the average atomic mass. And then I just go to my periodic table and figure out what it is. And depending on the masses of things around 90, you might not even have to calculate this. But we're going to calculate it just to calculate it. So atomic mass of 90, we said was 0.52%, plus 91 was 12%, plus 92 was 18%, plus 94 was 18%. And when I do that, I get A good question. What do I get? 90 times 0.52, 46.8 plus 10.92 plus 16.56 plus 16.92. Add all of those up. Oh my gosh. Okay, one day I will learn to do videos with my calculator in the room with me. Not today. 91.2 is the average atomic mass. And so we'll go to our periodic table. I'm looking for 91.2. Boom, right there. It is zirconium. And that's mass spectroscopy. Not super complicated. You just need to make sure that you're reading your graph. Don't let your percents go over 100. And do your average atomic mass calculations. They really are not that tricky in trying to mess you up. And then always make sure percent compositions match up with the periodic table. As I said earlier, with nitrogen 14 and 15. You shouldn't be telling me that nitrogen 15 is 50% of all nitrogens, because that's wrong because of its average atomic mass. And that's all.